Hi guys, welcome back. We're taking a look at some notes today. We're starting something new. We're starting parametric equations, which may be completely new for some of you. So this entire first section is just kind of like a recap to what are parametric equations and how do parametric equations work. Like, how do we graph them? How do we eliminate the parameter? How do we create them? All right, so what is a parametric equation? What is a parametric function? So here's our normal rectangular. So that usually we use rectangular coordinates. And this would be the function for some sort of object propelled into the air at an angle of 45 degrees with an initial velocity of 48 feet per second. For those of you in physics, you could probably resolve that force and whatnot. So we got this 45 degrees and so on. It's going 48 feet per second. We'd resolve that into an up force and a horizontal force, which is where we get what we call our parametric equations from. All right, so they are just equations in terms of a third variable. So we introduce another variable t. In this case, t would stand for time. And we get x as a function of t and y as a function of t. And together, these make points x, y. So this set of parametric equations, these two equations together, would give us a list of points that would exactly match these points that we get from this equation. All right, so that's how parametric equations work. And parametric equations also have a direction. So like we start at a certain point and we go in a certain direction, right? Because in this case, we're working with a projectile. That makes sense. All right, so how do we graph these parametric equations? Well, one way to do it is to just plot points. So if we're given these two parametric equations, x equals something in terms of t and y equals something in terms of t, and we have some sort of interval, we could just plot points on that interval. Like if we plug in -2 for t, so we start with t values, we'd get 0. If we plug in -1, we get -3. If we plug in 0, we're going to get -4. Plug in 1, we're back to -3. Plug in 2, we're at 0 again. And if we plug in 3, we're at 9 minus 4 is 5. So those are our x values for our points. And then we plug into y, and we got -2 over 2 is -1. -1 we plug in, we get -1/2. 0 we plug in and get 0. 1 we plug in and we get +1/2. 2 we plug in, we get 1. 3 we plug in, we get 3/2 or like 1.5, and so on. All right, so you could graph that just by plotting points. All right, so we start with, again, these make up our points, the x and y together. The t's now, we're done with them. We don't really need them. All right, so we've got 0 on the x-axis, -1 on the y-axis. So right there is our first point. The next one, we've got -3. So that's like way back here. And oops, I didn't want to put a point there yet. -3. And then down 1/2. So there's our next point. So we're kind of going from here to here, like that. All right, then our next point is -4, 0. Now I can put a point there. And again, we're going along. I'm putting little arrows to let me know what's my direction. Then -3, +1/2. And then 0, 1. So call that 1. And again, we're going this direction. And then we're at 5, 1.5. 1, 2, 3, 4, 5, and a little bit higher. And we're still going that way. All right, so to me, this kind of looks like a parabola on its side, and that's exactly what it ends up being. We can also do this on our calculator. We just have to change the mode to para or parametric, depending on what calculator you have. And you may need to go to your window to set the t values on your graph. So let's take a quick look at the graph or the calculator here. So if we turn it on, if we go to mode, right next to second mode, and if we look right here, it says parametric. It also has some other stuff, but for now, parametric. And now if we go to y equals, it says x with a little t and y is a little t. So like we could say x is, and we use this button here, we still use what our x is, and it gives us t now because it's parametric. So t squared minus 4, and y is t divided by 2. And if we graph, I don't know what I'm doing with my graph picture here. It's all sorts of weird. Zoom 6 maybe? There we go. All right, so it's only giving us the top half because it's starting at 0 and going forward. So if we go to window, all right, we can set our t values, t min, t max. So our t min was -2, and our t max was 3. And you can set how often you step or things like that. And you can set the regular window, the X and Y, just like before. And there's our picture, which looks pretty similar to that right there. All right, so that's how we can graph in parametrics. All right, so now we can also switch from parametric equations back to rectangular equations, back to just X and Y. The way we do that is we solve one equation for t, and then we plug that into the other equation and simplify. We may want to solve for y or whatnot. But here we have the same equation we had last time. We can solve this for either x or for y. It's probably easier to solve for over here for t. So we just multiply up the 2. We get 2y equals t. So now we can take this 2y and plug it in for t in the other equation to eliminate that parameter t. And we'll get x equals 2y squared minus 4. And now we've done it. It's eliminated. But usually we want to solve for y or for x or something, make it look a little prettier. Like we could square this out and say 4y squared minus 4. Let's see, we can add over the 4, divide by this 4 equals y squared. And then we can take the square root. So we get plus or minus the square root of x plus 4 over 4 like that. And then again, it would depend on what values you're going to get based on the t values here. All right, so we saw before x went from, what did x go from, 0 to 5? All right, so there if we eliminated the parameter, honestly, any of these would be fine. Like you could be fine to stop right there or to stop right there. That would be fine, either one of those. Even the first one is technically not incorrect. That's right. All right, next down, another example. Let's try something a little more difficult here. All right, so again, we've got x is something in terms of t, y is something in terms of t. Since there's 2 t's here and just the 1 t here, let's try and solve for that t. All right, so the first thing I want to do is get this off the bottom. So I'm going to flip both of these. So I'm going to say now we've got 1 over x equals the square root of t plus 1, just by flipping both sides. We can do that. Square both sides. And then subtract the 1. Or, well, I guess, yeah, subtract the 1. So there's t in terms of just x. So now I'm going to take this guy and I'm going to plug it in here for t. Both spots I have t. So I get y equals 1 over x squared minus 1. And on the bottom, I've got 1 over x squared minus 1 plus 1. Right? Minus 1 from here, plus 1 from that. So these ones cancel out. I can just flip and multiply this guy. So I get y equals 1 over x squared minus 1 times this guy flipped over, which is just x squared. And if I bring that through, I get y equals 1 minus x squared. And that's be much easier to graph than trying to graph this parametric equation. And this is just a parabola opening down, shifted up 1. All right, so that's one way to get rid of a parameter. There are some other ways, especially when it involves trig functions. All right, so here's another one. This one involves trig functions. So it would be very difficult to, well, it wouldn't be super difficult, but we'd end up with arc cosine or arc sine in our function if we solve the parameter here. So oftentimes, if we're working with trig functions, we look for some sort of trig identity relating the equations that we have. All right, so for instance here, we've got cosine and we've got sine. Is there a trig identity that involves cosine and sine being equal to, I don't know, say a number? In this case, there is. We have sine squared theta plus cosine squared theta equals 1. Most of the time, the ones we want to use are the Pythagorean identities, and this one is the one that comes up the most, the sine squared plus cosine squared equals 1. All right, so what we do then is we solve for the trig components. All right, so we could solve this for cosine. So we get cosine of theta equals x over 3, and we can solve this for sine. Sine of theta equals y over 4. And then we could say, okay, well, we can just plug this in for cosine, and we can plug this in for sine. So we'd get y over 4 squared plus x over 3 squared equals 1. So if we just distribute the squared here, we get y squared over, I'm going to actually just leave it as 4 squared plus x squared over 3 squared equals 1. Now, I don't know how far you got in your pre-calc or your math analysis class, but this is the equation of an ellipse centered at 0, 0, because we don't have anything being subtracted from this x or this y squared. And our axis lengths are 4 and 3. All right, so it would look something. Let's see, centered at 0, 0. We're going 3 in the x direction, 4 in the y direction, I think my y direction is not quite as spaced out as my x direction, but it's going to look something like that. So it just makes almost like a circle, but it actually goes up and down a little bit higher than it goes left and right. Should have made this not quite as long, but that works. But that's how we eliminate the parameter. So this getting to here was the important part, guys. So if you know to say, okay, sine equals cosine equals sine squared plus cosine squared equals 1, plug them in, there we go. We've eliminated the parameter. All right, creating parametric equations. So now we know how to get rid of the parameter. How do we go back the other way? So one way to create a parametric equation from rectangular coordinates, so from like y equals f of x, is to let just x equals t, and then we get y equals f of t. That's really basic. Like for instance here, if we have y equals 1 minus x squared, and we want to eliminate the parameter x, we could say, all right, well, let's let x equals t, and then we would just plug in t here, and we get y equals 1 minus t squared. Not very exciting. But we could let x equal almost anything we wanted to, and then we could plug it in here, and we could get another equation. Right? Another way to do it. So more complicated, there are more complicated other ways, often involve solving for a variable and then plugging in for that variable. So using the slope m equals the derivative at the point xy. All right, so we're still working with this equation. So the derivative of that equation equals 2x. So we could say 2x equals m, the slope. All right, so if we solve this for x, we'd get x equals m over 2. All right, so now what's y going to equal? Well, y is going to equal this equation, 1 minus, and then we're just going to plug in m over 2 for x. All right, so we get 1 minus m squared over 4 for our other equation. So these are now our equations. And we're using m instead of t. No big deal. If you want to switch to t, you could do it with t. I mean, you could just say, okay, x equals t over 2 and y equals 1 minus t squared over 4. And that would still get you the exact same equation, but then it wouldn't give you it in terms of the slope that we wanted. All right? But again, this would also be the same equations that these would be. All right, so there's more than one way to write parametric equations. All right, so that was just a brief overview of parametric equations. There are plenty of those to practice on the homework. The next section will look at parametric equations and calculus techniques like derivatives and integrals.